Welcome to our presentation on binomial distribution. Today, we will explore this fundamental concept in statistics. We will cover random variables, the central limit theorem, and binomial distribution. Let's dive into each topic one by one. A random variable represents a numerical value associated with each outcome of a probability distribution. It can be discrete, with countable outcomes, or continuous, with uncountable outcomes. Discrete random variables include the number of pink marbles in a bag or the number of heads when flipping a coin. Continuous random variables include the height of students in a class or the time it takes to complete a race. A binary variable has two possible outcomes, like success or failure. We can transform a random variable into a binary one by defining specific outcomes as success and others as failure. A random sample is a subset of a population where every member has an equal chance of being selected. This helps in reducing bias and ensuring reliable statistical analysis. A statistic is a numerical value that summarizes a sample from a population. It can represent measures like the mean, median, or standard deviation, helping us infer properties about the entire population. The central limit theorem states that with a large enough sample size, the distribution of the sample mean will approximate a normal distribution, regardless of the population's original distribution. Here, we see the formula for the central limit theorem. As the sample size increases, the sample mean's distribution approaches a standard normal distribution. This slide shows how the distribution of average scores from throwing dice approaches a normal distribution as the number of dice increases. Let's consider the average life expectancy in the world as of 2018. The distribution is not perfectly normal but is left skewed, demonstrating the central limit theorem in action. By taking multiple samples from a population and plotting the distribution of each sample's mean, we get the sampling distribution, which shows a normal distribution due to the central limit theorem. A binomial distribution involves n identical trials, each resulting in success or failure. The probability of success is constant, and trials are independent. For example, flipping a fair coin 5 times to find the probability of getting exactly 3 heads. The Bernoulli distribution is a special case of the binomial distribution with only one trial. It represents the outcome of a single experiment with 2 possible outcomes, like flipping a coin once. The expectation and variance of a Bernoulli distribution can be calculated using these formulas. They help in understanding the distribution's behavior. For a Bernoulli distribution with a probability of success of 0.4, the probability of failure is 0.6. This bar graph visually represents these probabilities. The probability density function for the Bernoulli distribution is shown here. It helps in calculating the expectation and variance for different probabilities of success. The formula for binomial distribution calculates the probability of getting a certain number of successes in a fixed number of trials. It considers the number of trials, successes, and the probabilities of success and failure. In this example, we calculate the probability of Ali guessing the correct answers to a 10-question multiple-choice quiz. We find the probability for 1 correct answer and all 10 correct answers. Here, we calculate the probability that exactly 4 out of 10 babies are male and the probability that at least 8 are male, given that the probability of a baby being a boy is 0.51. In a college, 20% of students are girls. In a random sample of 5 students, we need to find the probability that there are at most 2 girls. Using the binomial distribution formula, we calculate the probability for 0, 1, and 2 girls and sum them up to get the final probability of 0.94208. Cross-fertilizing a red and a white flower produces red flowers 25% of the time. When we cross-fertilize 5 pairs of red and white flowers and produce 5 offspring, we need to find the probability that there will be no red-flowered plants. Using the binomial distribution formula, we calculate this probability to be 0.237. Continuing with the cross-fertilization example, we now need to find the probability that there will be 4 or more red-flowered plants in the 5 offspring. By calculating the probabilities for exactly 4 and exactly 5 red-flowered plants and summing them up, we get a total probability of 0.031. An FBI survey shows that about 80% of all property crimes go unsolved. In a town with 3 such crimes, we need to find the probability that at least one of these crimes will be solved. Using the binomial distribution formula, we calculate the probabilities for 1, 2, and 3 crimes being solved and sum them up to get a total probability of 0.488. In a roulette game, the wheel lands on each digit from 0 to 9 with equal probability of 0.10. We need to write down the expressions for calculating the probability of getting the digit 5 or 6 exactly 3 times in 20 spins, and the probability of getting a digit greater than 6 at most 3 times in 20 spins. For the first case, where the event is getting the digit 5 or 6, with a probability of 0.20, we need to find the probability of this event occurring exactly 3 times in 20 spins. Using the binomial distribution formula, we calculate this probability to be 0.2054. For the second case, where the event is getting a digit greater than 6, with a probability of 0.30, we need to find the probability of this event occurring at most 3 times in 20 spins. This means calculating the probabilities for 0, 1, 2, and 3 occurrences and summing them up. Finally, we sum the probabilities for getting a digit greater than 6 exactly 0, 1, 2, and 3 times in 20 spins. Using the binomial distribution formula, we find the total probability to be 0.1079.